This is a re-recording of the presentation I was giving at the graphics programming conference in Breda. It's called Shader to Human, or S2H in short. And it allows you to visualize the internal state of your shaders. It runs in HLSL and GLSL and should be easy to integrate. There's 3 use cases on the screen. You can see on the left, there's a vertex shader and a pixel shader projecting a quad onto the screen. And then in the pixel shader, it uses Shader to Human to print out parameters that you normally wouldn't see. In the middle, you can see a 2D use case where a compute shader was just invoked to print out some text, and it can be useful for a post-process as well. On the right side, you can see the 3D functions that are in the library. They allow you with some kind of simple ray tracing to visualize 3D objects in space. This was mostly made by me while I was working at Seed Electronic Arts, and we used it there, and Anushka Nair also contributed to the project. If you want to find it, you can use that link, or you can just Google Shader to Human. You should be able to find the GitHub repo very easily. You might use printf in C++ or other print functions where you can print out the internal state of some variables. That's basically what you can do with it. In other environments, like if you have an IDE, you might use a debugger. That's also similar to it, but debugger is more convenient because you can quickly change something without having to rerun the application and recompile it. And if you have an environment where you have hot reload, then this is more comparable to how a debugger works because you don't have to quit your application. So shader hot reload allows you to just make a few changes, like print out a different variable, for example, and then you can just see what's the state of that new variable. So it's more comparable to a debugger window, but it has these printf kind of properties of you can style your printout how you want to have it, so it's more suitable for your debugging purpose. So there's multiple functions in it. You can do 2D things and text, or you can do 3D, some simple primitives like lines and cylinders and all that. But there's also a few UI functions that allow you to make buttons and checkboxes and radio buttons as well. I want to be mentioning that performance could be a problem. So if you're using a lot of text printout, it just accumulates more and more complexity in the shader, and so it gets slower. You could render the same things faster, but it's not optimized for performance. It is optimized for ease of integration. And that is very important. So if you want to use that at a runtime for a game, I wouldn't suggest it. But if you want to use it during debugging for when you're doing it locally, I think if you know what you're doing, this is even what you see on the right side, it looks like a lot of printout, but that still runs very fast. So you shouldn't have a problem unless you want to use it in a production environment. So it's very easy to integrate. With HLSL, it's just a few includes, maybe only a single include, depending on which functions you want to use. And you can also use it with GLSL. There is a little include that has a few defines in it that remap functions that would normally be in HLSL form, make them compatible with GLSL. You can use that, or there's other options too. There's unit tests that are integrated in the GG framework, and it makes screenshot comparisons. So it's also fairly stable, and you should get good results, and it's pretty predictable of what outcome you get. If there's new versions of the library, then we try to make it as much compatible to the old one, but I don't think you will have much problems. So where you can get it, as I said, you just Google Shader to Human, then you can find that link. It's on GitHub and you can download it, but you don't have to look for everything. It's just the include folder that you need for your own code. The other things are documentation and automated tests and other things. You can also use the GG browser. So GG is a framework that was made at Electronic Arts, the C team, mostly by Alan Wolf. And I contributed a little bit as well, but you can use GG to have a hot reload environment where you use HLSL and DirectX under Windows, and that's what I would suggest if you want to play around with it. But if you want to integrate it in your own engine or your engine that you have to use because of work, that should be fairly easy because it's just made for ease of integration. ShaderToy, you can use it too. If there's the common tab in ShaderToy, then you just paste it in there. It should work too. So in my personal experience as a programmer, I went through multiple phases and stages and all that, and I learned a lot. And in the end, this was leading to this library. So I want to tell you about that. So when I did C++ programming, I used the debugger or I used printf debugging. That's as usual. And then if you're having, in CryEngine, for example, we had a complex environment with a lot of GPU programming and other things. So there it was very handy to visualize the internal state of textures. So implementing visualized texture was a very handy tool there. But we also had console variables and we had Lua and C++. And it's always hard to see the internal state of those things. You might have to use different functions, and it's just a little bit hard to see what's going on inside complex systems. In Unreal Engine, first from 3 and then at 4 at some point, it's the same situation, and we embraced more and more those kind of visualizers, which are outputting to the screen the internal state of the system. And you can see on the bottom right here, this is the tone mapper visualizer, and it's in the middle here, it's kind of zoomed in and small. It was printing out some numbers, and this was the first version of printing out numbers in a shader, and it actually works by using the pixel shader. The pixel shader figures out where in a 8x8 grid it is, and then it computes which number or character it should print. So based on, there's an input floating point number, and then it figures out which digit you are and which digit it actually should print. And then it makes a lookup into a small font table or texture, and then it can print this text. That's how it originally worked. If you want to implement something like that yourself, you can use Shader to Human now, because that complexity has been abstracted away for you. So you don't need to reinvent the wheel. And in this case, you don't even need a texture. You don't need to bind another texture, which adds some complexity to the whole integration. You can just use the shader because the texture is embedded in the shader. That makes it especially convenient. But you don't have to use that feature. You can still use a texture. That's an optional thing. So at Meta, we had a situation where we had Unity, and we wanted to make the Unity math library in C++ as well, so kind of having a consistent result either through Unity or that C++ library. And in order to make that correct, you had to compare the transform operations that were happening on the Unity side in C# and the transform operations that happen in C++ side. And just to compare, you kind of need to look inside. You need to see that. And the same thing should happen in your math library as well in HLSL. So you're like, I wanted to look inside, and you kind of have to do that, and you have to make those comparisons. Only then you understand it fully. And it got even more low level at when I joined Electronic Arts at the C team, where we do GPU driven rendering and persistent thread. And you see the complexity, the depth of inside the GPU to figure out what's going on in this multi-threaded environment is really complicated. And so debugging was even more necessary. And you cannot just use read back, that would cause performance problems, and you want to print it out directly onto the screen and see directly. And sometimes you need those numbers and sometimes you need the other numbers. So we identified tooling is needed, and that's where Shader to Human was made for. There's a good documentation that you can browse, and it is implemented in HTML. So you can click around and see the different functions that the library provides you with examples. It's the idea was to make it a little bit like the Borland C++ documentation, which had always a few snippets that you can just copy and paste, and then you can use it in your environment. And you can also see that there's a little preview, and that preview is actually rendered with GLSL and in WebGL. So this is where Shader to Human is actually used. So this is not images that have been offline generated. This is actually running in your browser, and also proves that Shader to Human even runs in WebGL in GLSL there. And if you want to copy and paste it, just there's a button here, you can copy the code, and it can be very handy. The thing is that WebGL doesn't have a defined support or preprocessor support. So what we do is we have a little batch file that we can run, and when it runs, it finds a preprocessor, and converts these defines that we use in the library over to a non-defined version, which is also possible. So it does manually unwrap those basically, or apply those ones, and then it can be used in this environment. So if you have an environment where you also don't have a preprocessor, you can also use this method, and then you just use the GLSL files. Otherwise, you would use more includes, and there would be defines remapping the existing HLSL code. The whole library is made in HLSL, but then it remaps it to GLSL with those few defines. The documentation of Shader to Human is in HTML. You can see here how this content can be rendered with just those few lines of code. You have to include the library, then you have to create a struct, you initialize the struct, and this is all for the content. So you can change the color, you can change the size, you print some numbers, text, whatever you want. And then you have in UI.destColor is the final color, and you just output it with your pixel shader. In this case, that's the GLSL code. But if you change here to HLSL, then it generates the HLSL code for you. And in this case, it's a compute shader. So it looks a little bit different. The syntax is slightly different, but the library still works for both. If you want to see, it's actually interactive. So you can here have some basic camera controls. So if you open the GG viewer with the features technique, you can see different passes. And here is one pass that shows how the ray tracing works. So there's multiple little objects being pushed. And then for every pixel, it intersects with those objects and figures out which one is the closest one to the camera. It renders that for you. So you just have a few function calls. And here's a function call to actually print the X, Y, Z position of the camera to the screen. There's more 2D things that you can print out, any kind of text in different size, different colors, little squares, little circles if you want to. But you can even make an interactive UI if you want to. So Shader to Human tests the mouse position against those UI elements, and when you're clicking on them, you can update some state. So like this checkbox, or you can update a float if you want to. You have to store this information of the UI state somewhere. In this case, it's stored in a struct. And if you're just updating those struct values, you can have other passes using those ones and rendering those ones. If you want to make more complex UI, you can use lines, circles, use the mouse position, visualize half spaces, move circles around. And here you can see how our sRGB sRGB gradient is being shown. That can be useful to debug your 8-bit color precision issues. And if you want to use the compute shaders, then sometimes you want to visualize for a given lane of a compute shader or a thread. You want to visualize the values that you have in some temporary variables. You can do that too with the scatter operation. So this time you're not computing a color based on an XY position. You're actually poking or writing a color into a given location on the screen. That's more how you would do it on a CPU. And that's something that can be useful when you have a compute shader and you want to visualize the different properties of a thread. Last one here is if you want to, you can also have here a quad being floating in 3D space. And in this case, that quad can also visualize, can also show 2D UI. You see that here, it prints out some numbers here. You can attach some quads to your weapon and fly around with it. And you can debug things like this. Here it prints out different positions in tables. So this sample shows a fractal being rendered. And you see it's in grayscale here, but if I zoom in, you will see some color artifacts. And that's because the red channel is actually computed in lower precision, like 16-bit float. And you see it doesn't look good enough anymore. It's low precision. But if I zoom in further, you can see the quality degrades further. Even the green channel, which is computed in floating point 32-bit, is also not good enough, but the blue channel still looks good. So that's double. So I have 3 different passes that computed in 3 different precision levels. And in order to profile that one, I can use the new feature that we have in GG, where it's using the NVIDIA backdoor to query the time in the shader, and then it writes the time into a struct, and then we can read that back and we can visualize how long it takes to render those passes. And you can see the numbers are printed here in milliseconds. And if you want to know that information about how long something takes for a wavefront, then you can also see this visualization here behind it. You see this heat map that shows you for a quad that is consisting of two triangles, how it was rendering this fractal as well. But this time you can see visualized how long it took to render that part. And this color, this visualized color, is also used to build a histogram. And this histogram you can either visualize here as a 2D function, or you can just read the numbers. So you can get a lot of information visualized with Shader to Human. So Shader to Human is really optimized for ease of integration, as said, but in different environments you might have to do a little bit more work. If you're lucky, you have HLSL and you have a preprocessor and you can include files, then you just need to copy over one file potentially and then include it, and then you can use the library already. If you want to use 3D features or the scatter, which is useful for Compute Shader, then you just include 2 more files and that's it. So you're best off with this method if it works for you. But if you, for example, if you need GLSL, there is a remapping defines in this file here. So you just include this before, and then you're getting everything remapped for Vulkan or OpenGL, and you have GLSL, and that's a convenient method too. This remapping doesn't cost too much per time actually, and that's also pretty good. Now, if you're unlucky that you don't have an include, then you kind of need to copy over those things. In the case of ShaderToy, for example, it has a common tab where you can copy and paste that kind of code. So I guess you have to do that there. This gets more complicated down there, but usually you just find the easiest one for your purpose. Now, if you even don't have a preprocessor, for example, for WebGL, you don't normally have a preprocessor, then there's a batch file that calls, you don't have to call it anymore, but you could call it if you change the code here. That batch file converts all of those HLSL codes and applies the preprocessor, and then you get GLSL files out of, and so you can directly include those ones. So that also works, and that can be done in WebGL, but you still need to support somehow includes, and that could be slightly more complicated depending on how your web HTML setup works. So that might work out for some cases, but if there's other cases where you have to really have all the source code in one single file, then again, you have to go back to copy and paste things. So you might be wondering how we implemented text printout inside a shader. Normally there's no access to the font, and so you would have to implement it yourself. And you could do that by providing a texture and then make a lookup into this texture. But that way is a little bit difficult for integration, because it means you would have to change C++ to upload this texture, to bind it to the shader, and that adds a lot of complications, and it doesn't provide you with that convenient just including and changing a shader. So you can use this method. There's a define if you want it for control and maybe performance, but otherwise just use the default that is built into, which is a table. In that table, it has a bunch of numbers, and then it just reads from that table those numbers. And we had to iterate on the code a little bit to find a good path for the drivers, but we're happy with the solution and it works pretty well. If you're doing it with the wrong keywords outside a function, inside a function, you can get into a slow path, but we found a good solution for our test cases, and we're happy with it. But if you're using it on some maybe older mobile GLSL driver, I mean, you could have a problem. Just keep that in mind. So the data is stored in 32-bit, and so it has to unpack a little bit, and there's some integer operations, and that's also partly why it is a little bit slower. It has to do those kind of things. A texture lookup would be faster, but it's not critically a problem for us in modern GPUs. We're also trying to avoid defines and templates just to avoid some complexities, but you will see that for certain cases, defines are useful, for example, to remap from HLSL to GLSL. So here you can see some use cases of how you would print a character. You see that we pass down this UI variable, and that is storing the state of the color of the pixel where you are right now. So every function that you call is basically figuring out, is that pixel that you are right now at, does it need to be altered? figures it out because it has internally a state of where the cursor is. And then based on what character you're printing and what's in that table, if there is a pixel that says here is the font has a white or a black pixel, it can figure out if it should update the pixel where it is right now. And 65 is a number that is a ASCII code character, and that will work. But that's obviously not very convenient. So if you want to use it more conveniently, you just do print text, and then you can print out multiple characters one after another very easily. And this one works in HLSL, and that's acceptable if you use HLSL. But if you want to have it for GLSL working as well, then you use the defines. There's an underscore, or actually it's a const static, remapping these symbols _x and _0 and underscore space and so on to a number. And this way it works in GLSL too, because it doesn't have this character literal like here. Now that's still a little bit inconvenient. So in theory, if you want to print text, you kind of want to have something like a string with just double quotes here, but we don't support that yet. It is possible in some HLSL variants, there's newer and older ones as well, but then it would not be portable anymore. So we don't have that right now, and it could be added, but then it still would not be portable. So I'm suggesting at the moment this method, because that would work everywhere, and that's what we do. And if you know that you're only in HLSL, then you can also use this method easily. And then if you want to have to go to the next line, you print a line feed. So there's one very important concept you have to understand to use the library effectively, and that is how the gather functions work. I explained that here, and there's also scatter functions, and those ones are more a special case that you might use in some compute shader cases, but normally stick to the gather ones. They work for compute pixel shader, and they're more efficient and easier to use. So the whole thing, how it works is you're after you included the library, you're creating a variable called UI with the type context gather, and then you're calling the init function on it. All the functions usually start with s2h underscore, so you can identify that they belong to this library, and then you pass in as first member this variable. This could have been UI dot, and then you would use member functions, but that would not work in GLSL, so we decided to make this more portable and easier to use across GLSL and HLSL. So it is, you pass it as a first parameter. It's passed usually with in-out, so that the UI variable can be changed by this. For example, the init function will set the cursor at the left top, and it will also use this pixel position. So when after those two lines, the struct actually knows which pixel we're on the screen right now, so which pixel it needs to produce a color for. And then in the end, what you have to do as the caller, you have to extract from that struct UI.destColor and apply that on top of your existing color. So if you have a tone mapping shader, for example, in the end of the tone mapping shader, you composite the UI.destColor, which has an alpha channel as well, on top of your existing color, and is all done in linear space. And so if you need it in sRGB space, then you call another function. That's what you have to do usually. And then here in that ... area here, you would call functions that draw something on the screen. You can set the cursor position, which is just changing an internal state in that struct. You can change the scale, same here. You can do a lot of things like the color you can change and things like that directly at the struct, or you use the functions. The functions, if they exist, you prefer those ones because they might do more smarter things than if you just change the internal state of this struct. But the more important ones are the ones that are printing something. So you can print text, you can print integer, hex, float, or other things. Those ones will internally figure out if the cursor position and the current pixel position are overlapping. If yes, then figure out what character needs to be printed at that location. Look up in the texture or into the array, what is the pixel? Is it a 0 or is it a 1? And then it will draw something there or not, and it will override destColor. So the compositing happens all for a single pixel in that thread, in that shader invocation, and then in the end you composite it. This is how gather works, and if you understand this concept, then you can use it easier. On the right, there's some examples. So this is zoomed in already. I think I was implementing something that with the mouse, you can hover over some pixel and you can see the pixel position, and then it reads the red, green, blue. And here it's printed out in 0 to 1 range as well, even the alpha channel. It's a handy kind of debugging tool here. This is just printing out something from the automated unit tests, and these pixels are getting compared by the unit test to always look the same. So there's even for the printout for floating point numbers, it can also print out none. So you know if something is internally not a number, and that can also be very useful. So you know how to print out text, but if you want to draw some shapes, 2D shapes, then you can use those 2D functions. And they're still in the same HLSL file, so that makes it convenient to use. The same setup can be used, and you just call into different functions. They start with s2h_draw, and then you can draw those things, and they have different parameters, and so you can draw whatever you want. One important thing here is because they are often anti-aliased, so you get some shades on the borders to kind of make them appear softer and not aliased. You don't get those stair-stepping artifacts from not anti-aliased rendering. Because they're anti-aliased rendered, you need to care a little bit more about the colors. Before that wasn't important, and I mentioned there's a linear to sRGB function that you want to call, and that's the reason why you want to call this function. For text, it wouldn't be important, but it is important if you want to draw something with anti-aliasing. So just keep that in mind. That's why you call this s2h_linear to sRGB function, and you still want to do the same things as before. So the functions, you can use draw rectangle AA for anti-aliased, draw line, crosshair, half space, arrow, and there might be a few others like triangles as well that you can use. There is 3D functions, and those ones are actually in a different include file. So we want to include that file additionally. Then you can also draw 3D objects, and that works by using ray tracing. It's brute force ray tracing, meaning there's no acceleration data structure. It just iterates through all of the objects that you have. It's just the function calls that you're making, and then it finds the one that has the closest intersection and keeps that color. So it does correct visibility, and if you're putting everything into one function, the scene, if you put it into one function, you can call into the scene a second time with a different array intersection and implement shadows. So this was done here. You can see there is this checkerboard here, which is one handy function call actually. It's called draw checkerboard. So you can put it at a certain position, and it already has an arrow, a red and a green and a blue one. This is kind of an arrow that points upward. That's assuming that the y XYZ is red, green, blue, that the y vector is going up. So this is already a coordinate system, and you can use that handy for your own debugging of 3D objects. And you can see what's the distance and the size and everything, and if your camera matrix works correctly. So this is already very handy. And you can see here that here's that shadow casting that I was mentioning. You can draw some axes, but it's always convenient to know red, green, blue is XYZ. And in this case, the library has the assumption that green is up. But I think if your environment that is not the case, then I think you can change it very easily. But if you have trouble, please contact me. I think we can make it maybe a little bit easier with a define or something. So if you want to set it up, you have to do slightly different calls. In this case, there's a context 3D struct, and then you make that context, and you have to still call an init, but this time you need a ray. So you have the ray origin, which is the same as the camera position, and the ray direction. If you have to compute this one, this depends on your environment. So you need to figure out how to compute this ray direction, but it shouldn't be too hard. And this is generally an easier setup than a lot of vertex shader, pixel shader things. So once you have that setup working, you can debug with this, and then you can also verify if your other projections work the same way consistently, and so you can compare it. So this is a nice way of debugging. And if you want to know if your objects are transforming the right way or something, you can just draw in world space things into this thing, into this environment, and then you can debug it very easily. So you can draw arrows. A basis vector is just this red, green, blue here. And then a sphere you can draw in world space. and you just pass down those parameters. The checkerboard is handy for having something to ground you so that you know what is up, what is down, and then what size it has. On the right here, there's another example. In this case, it's an axis-aligned bounding box, and that one has edges, and each of those edges, I needed to know what is for each of those edges, what are the two planes that are on the edge. And so they have a vector that is pointing in the direction of that plane. And with those two planes, I can figure out if an edge is an edge that is inside, here in 2D, or is outside, that's the border. Because in this case, I was interested in a shape, a 2D shape, like here, this convex hull in 2D that this bounding box is forming. So by having for each edge those vectors makes it easy to kind of identify which edges are relevant for me that are forming this outside polygon. And then I have only those edges. Then I can take the plane equation, and there's a visualization for 2D plane equations as well. I think I showed that before. Yes, here. So you can see this is a half space visualization in 2D that shows how those planes work. They're a little bit offset deliberately so that it's easier to kind of see, but that visualizes those planes. And then I can easily, with a few tests, figure out if this pixel is inside this object or not. So this allows to kind of make a test if a ray intersection with this shape would happen in 2D, which can be more efficient. And then you can answer that with for a low resolution grid as well. So this can be handy. It was one of the applications that I used. Oh, I guess I should show here for 2D. There's some user interface as well. So there's functions to kind of draw these little sliders, and you can drag them around. If you pass down the mouse position, which is another line of code you have to add, then you can move those sliders around, and you can change some state, and that can change the colors or whatever you want to drive with those sliders. Especially if your environment doesn't have a convenient user interface to pass down these kind of user elements, then that is handy to use. But you don't have to use it. So if possible, you should use the gather function. That's true. But there's cases where you cannot use them, and then maybe the scatter functions will work for you. So that might be either if you're on a vertex shader and you just don't have pixels in that case directly accessible to you, or if you're in a compute shader and you're not outputting to a 2D texture, then how can you get your text out, right? So there is a way to do it, and in this case it is scattering or poking or making a random access write operation into another texture or 2D buffer. And for that, in DirectX terminology, you call it a UAV write. And so you need to bind that additionally. And once you have that bound, it has a certain size, then you can just write text into it. But every thread is writing the full character and the text that you ask it to write. So if you write a lot, then this can get very slow very quickly. And also you cannot read it because it's all on top of each other. So you need to be careful to filter it out properly. In this case, you still want to include the usual shader to human, but then you also include _scatter as well. And then you need to implement one function that is a bit different. So this one function is is how to implement the scatter operation. The system doesn't know, or shader to human doesn't know which buffer you want to use for output. And so you can just have this little function called, it's usually just 2 lines, where it outputs this one color. And if you want to have that in a different buffer, then that's the function where you would change that. You still have a struct, and there's an init for that one, but now you no longer tell that struct which XY pixel position you're writing, because every thread is writing its own data through this function. So you can put this one into your HLSL file, and that implements various output. And if you have a different shader where you use a different binding, then you can have a different name here as well. So there's functions for that. They look very similar to the gather functions. Like you can still set the cursor and scale and print and all that stuff, but they do more work now because every thread has now to do more work. It prints a whole character, it goes through the whole floating point number and prints out each of those characters. Now, if you use it the first time, you might accidentally just have a lot of overdraw because all the threads that want to maybe print different things are all on top of each other. So the first function you want to call is the setCursor function, where you pass down, here in this case, for example, it's the thread ID. You pass it down here as for the X 0 and Y is thread ID multiplied by 8. This way you have them all separated out, and so every line here is for a different thread. So it allows you to debug what's going on in different threads. So here I have two variables like X and Y, X and Y, X and Y, X and Y, and I have a for loop that goes through these things 4 times here. And you see the first time on the thread 0, it has 1, 0. Then the second time in the for loop, it has 13, 2, then 18, 12, and then 23. And that was allowing me to debug multiple states for multiple variables for one thread. And also in parallel, I see how the other threads are doing. So this allows me to debug much more low level than the gather one would do. So use that when you have to use it. Here's also some printout very similar to the other one, because you just call the same functions basically, but now it does a scattered operation. This is more akin to how a CPU would do it, where you just go through all the pixels of the font and then you would output it like this. So it's less efficient, but it can be very handy. If you're in a vertex shader, you can use this method to kind of scatter out to a 2D buffer to kind of write something out. But if you're in a vertex shader, what also is an option is you're outputting the value that you want to debug to the interpolators, and then you read that with the pixel shader, and then you can do gather functions to output the value that was interpolated. But I would prefer this one, because interpolators have their own little rules about how interpolation happens, and you might have multiple vertices, and if you're not outputting the same value, the interpolator produces new interpolated values. So the debugging is a little bit less safe, but if you know what you're doing, that is another option. So everything mentioned so far is outputting, but how about input? The mouse, for example, could we be responsive to the mouse and click buttons, move sliders and checkboxes? And yes, that's possible. If you pass down the mouse position and the button state, then there's a few functions that you can use. Please don't use them as an immediate mode UI replacement like IMGUI, but you can use them for debugging, and for simple cases, it is appropriate to use. They're not polished for performance. They're not optimized for performance. They're not polished on visuals, but they work for your debugging cases, so that you don't have to recompile HLSL all the time if you just want to have a single state of, I want to visualize a different variable. So here's the functions, and they have different parameters, and that should be familiar to how it works in IMGUI. And what you have to do in every of those immediate mode things is you have to store the state. So those functions don't actually update the state. You get returned what you should do. And for example, the radio button, when you click on it, then you get back which state you clicked on. And if that happens, then it's your responsibility. It's usually a single line where you're just writing to another UEV with a scatter operation, that state change. And then if you're binding that buffer for the next frame as well, then this way you maintain that state. So it's on you to maintain that state. There's another thing to print out large amounts of numbers. You can print tables, and they are performance-wise much better than printing out, in this case, from here to here, that's 11 numbers. If you would print out print float 11 times, that would be slower, because this is costly. It costs as much roughly as a single float print, but because it figures out in which row you are first, then figures out what is that number that it wants to print, and then it evaluates this print float, so it runs more efficiently. So this costs about the same as a single print float, but it actually prints 11 numbers, and it's counting for these guys as well. So printing out tables can be handy to kind of debug the state of larger things. And you can make yourself a little hex editor or hex viewer, even an editor actually, if you wanted to. So it can be handy, but if you're overdoing it, don't be surprised if it gets slow as well at some point. You can also print out little drawing little functions, so it can be handy to kind of maybe your tone mapper function or something you want to visualize. So in the end, a few tips and tricks. So most likely if you use gather and you don't see the output, you just forgot to composite it. And make sure that you do that in the very end, so you're compositing the color on top of the existing color and not someone else is overwriting that color again. If you're using scatter, then make sure that you're offsetting based on the thread ID or based on the wave index. And also you should filter out a lot, because most elements you don't want to output. So if you're debugging only the first bounding box, let's say, that you're processing, then you can write if index of that bounding box equals 0 or whatever number, and you can hook that up to some user interface functions as well to kind of change that number interactively. But then you're outputting only that one, and that reduces the performance problem and also makes it more readable, right? One little tip is, if you want to implement something like an assert, which in C++ I like to do that a lot, you can do that in the shader. So it's more a trick that you can do anyway, as independent of shader to human, but I find it handy. Is you use an interlocked operation, so an atomic operation, and you just accumulate how often you're going into this code path. And then if you print it out with shader to human later, you see how many times this interlock has been called. Maybe every frame you're setting it back to 0. So this way you know how often you're going to that code path. So together with shader to human, you know how often that assert has happened. And now if you're wondering of where that assert has happened, like which node ID was causing my problem, you can probably use an interlocked exchange and can write into that value what that number is, and so you can debug that one. So that can be very handy. So it's kind of like an assert. I like to have a shader, a post-process in the end that basically reads that state, and if nobody writes it, there's no problem. But if somebody writes it, you know somebody was going into that code path that you want to know about. Make sure if you write your own functions that pass around the gather or the scatter, that you write in out in front of it, because very often they want to change the state of those ones. That just can happen if you start making your own functions. One handy thing I also found is very often for something like a ray tracer, in software ray tracer that you implement, you might have endless loops. And yeah, if your code is perfectly right, the endless loop is maybe appropriate, but very often you might get the graphics card hanging and you cannot debug it then anymore. So what's easy is if you just reduce or limit the amount of iterations. Maybe 200 is too small for the real case, but during debugging, 200 could be really handy, and then you can output when that case happens. You outputs the values of the state of the internal state that you want to debug, and this way you can, it's almost like a data breakpoint where you say, if that value is this, then output something maybe with a scatter operation. And there's a built-in feature that I added to GG at some point, which is using the NVIDIA hardware feature to kind of get the time in the shader. And so you just, if you include this, so it's a feature of GG now, then you can output or you can store the time in a variable. And that is very handy to kind of profile things, like which pixel took how long, and then you can visualize a color. That together with HLSL, together with shader to human can be very handy to profile something. So what's next? Here it says open source, but that was a long time ago when I wrote the slides. It is open source since quite some time now, and you can use it. You will find it if you just Google for shader to human. Can it be adapted to other engines? Yes, if they're already working the same way, there's no problem. You just use it directly, but maybe we have to make some adjustments. We don't have a lot of experience with different engines, so if you have any feedback of how to make it better, please tell us. There might be some other high-level features. For example, we could have something like a log file where you have a buffer that you're binding, and then you're logging just a few numbers into it that you want to output. And then there's another shader afterwards that maybe is some 80 by 25 text console window-like thing. And that one would print out whatever it finds in the log file. So you can actually output into a log file and then browse that log file with some functions. We don't have that yet, but would be possible. If you want to extend it, we could also record things like line drawings and other things into a buffer, and then they could be played back the same way with Shader to Human. So it would be more like a stateful thing, where the current Shader to Human is mostly a stateless thing. So it doesn't keep state, and that's also why it's easy to use and why it is convenient. But if stateful things are useful, then we should do it. The backends that we support right now is HLSL and GLSL, and different graphics libraries that use HLSL and GLSL should work, but it is a little bit more difficult in some environments because they include files and all that. So if we can improve on that further, please again give us feedback. It's really up to you what we do next here. So Shader to Human can be found, Google it, and then you only need the files in the include folder. All the rest is for documentation and testing. And there's some examples, and I suggest you play around with the interactive documentation or with the GG examples that come with it. GG is an environment that is very convenient for shader development. For Windows, DirectX was written by Alan Wolf and made in the C team. And I want to thank Anushka Nair also for contributing to this project. And please contact us and use it so that we can share in which ways this library is used and how we can extend it further. Thank you.